Hello, everyone, and welcome to this week's Scrum seminar. I'm Somdatta, and as every other week, we have two speakers today. Our first speaker is Dr. Souvik Chakraborty. He's an assistant professor at the Department of Applied Mechanics at IIT Delhi. He holds a joint faculty position at the School of Artificial Intelligence at IIT Delhi. His research interest spans a wide range of topics in scientific computing and computational mechanics, with a particular focus on analysis and design of stochastic systems using machine learning algorithms. He received his PhD from IIT Roorkee in 2017. Prior to joining IIT Delhi as a faculty, he spent 2 years at the University of Notre Dame and 6 months at the University of British Columbia as a postdoctoral researcher. In today's presentation, he would be talking about his new work, a graph-based data-driven solver for time-dependent nonlinear partial differential equations. Souvik, you may want to share your screen now, and you can begin. Thank you. Souvik, you may want to share your screen now.
Am I audible?
Yes, you are.
Okay. So thank you for the introduction, and sorry to hear the sad news about Bruce. So anyways, I hope his soul rests in peace. So let me share the screen. So I hope my screen is visible. Is my screen visible?
Yes, Souvik, it's visible. And you're
okay.
audible.
Okay. So yeah, so thank you for the invitation. So and thank you Somdatta for the introduction. So I will be talking about one of our recent work, which is on using graph-based learning or graph-based neural network for solving time-dependent PDEs, non-linear PDEs to be more specific, but it can also solve linear PDEs, but we are focusing on non-linear PDEs. So I will talk about the framework, and I will show you results that we have obtained, which are kind of exciting. But before that, let me quickly motivate that how this work was motivated. So we are engineers, right? And as engineers, we deal with PDEs on a day-to-day basis. I mean, if we look into the physical world, the physical laws are mostly in form of PDEs, or in an approximation sense, it can be ODEs. I mean, that is what we are dealing with. And this comes in different forms. So for example, on the left, there is a cyclist, and that is basically nothing but the Navier-Stokes equation that we are solving. Then in biomechanics, if we look into and if we try to find out the stresses that are being developed in the bones as someone is running or even cycling, so that is basically nothing but a solid mechanics kind of problem. You are solving the stress equation. And similarly, if you're trying to design something, same is the scenario. Now, I believe, and I will argue that we as researchers in the domain of mechanical science deals with only solving PDEs, at least the numerical portion of us, if we remove the experimental part. And that's what we are doing for last several years. Finite element method, finite volume method, you name it, all of these are nothing but methods for solving PDEs, time-dependent PDEs, time-independent PDEs, and so on and so forth. And the matter of the fact is, even after significant development over the past 50 or 60 years, there is still scope for improvement. So if you're trying to solve something using the numerical solvers that are well developed, be it finite element or finite volume, often you will need extremely fine maze. If it is a time-dependent problem, the time integration step is often very small, and as a result, the computational time is very high. Now, recently, over the past few years, we have started solving PDEs not only using numerical techniques, but also from data. So there is a boom in the data-based or data-driven solution of PDEs, and that is what we will be focusing on today. But if we talk about database solvers or where we use data, it is not like it is the perfect solution. I mean, it can give rise to a big data problem. You can have very large data set, and the other alternative is even more challenging maybe, and which is a slender data problem, where in the spatial domain you might have a sparse data, but in the temporal domain you might have a very fine data. So essentially, you have to deal with big data problem if we have sensors which are collecting data at high frequency rate. The data is often unstructured, and dealing with unstructured data is a challenge, is a significant challenge, and that is one of the aspects that motivates the use of graph, which I will talk shortly. The data is obviously, I mean, no matter what data you are working with, it will have some complex noise, outliers, and we're talking about deep learning or machine learning. And for big data problem, the training time can be significant. I mean, you can use GPUs, but still it can be significant. So this basically, so the idea is to work on or develop graph-based algorithms, because graph-based algorithms are very good in, or are ideal for dealing with structured data that is in form of graph, and that is what motivated us. Now, I was talking about graph, right? So first, it is important that I very briefly go through the graph. And so when I talk about graph data set represented in form of graph, I mean, it means that there will be nodes and there will be edges. The edges represent dependencies, direct dependencies, and the nodes are the variables or inputs. You can think of it like that. And the interesting fact is most of the data, real world data, are on irregular domains and can be represented using graphs. So for example, on the right hand side, I have shown a friend network on Facebook. So you can think that you have friend and your friend of friend, and that can go on. And this is kind of friend network. And you can see that if you're, I mean, this is not structured at all. This is an unstructured data, and graph-based algorithms are ideal for solving this kind of problems. So the idea is that as engineers, we work with unstructured data or meshes. We don't work on regular grids most of the time. So the idea is how can we use or bring the concept of graph learning or graph-based solvers into for solving time-dependent nonlinear PDEs. So that is basically the motivation. We want to bring graph and use it for solving in an efficient way nonlinear PDEs, time-dependent PDEs. So this is the outline of my talk. So I will start with the problem statement. So what exactly are we trying to solve? And then the proposed approach, which we call GrADE, has particularly 3 components. There is a feed-forward neural network, actually more than one feed-forward neural network. And then there is graph. And not only just graph, there is also attention, which is there. So I will briefly go through these 3 components. And then I will talk about in details about the architecture of the proposed framework. So it is kind of a custom graph network where you have to customize the graph network for the problem at hand. So there are certain parameters which needs to be customized, and I will talk about that. I will talk about the graph architecture, which is a sub component of the overall architecture of GrADE. And since we are talking about graph, training is like message passing kind of message passing is a common form of training. So I will talk about training as well. And then I will proceed to the examples. I will talk about 2 examples, basically, both same Burger's equation, once in 1D, once in 2D, and then we will summarize and conclude with some future directions to work on, because I believe there are several directions which needs to be explored. So what kind of problem are we trying to solve? Yeah, nonlinear time-dependent PDE, but we are primarily dealing with autonomous PDE. So time is not explicit here, time is kind of implicit. And the PDE, if we look into PDE, it will be, so when you see it in the suffix, there is t, that means time derivative. So u is your state variable. And then the operator f is on the right side, which operates on x, u, and the spatial derivatives of u. Then there is the boundary operator and the initial condition. So what are the data that is available to us? So we have a grid, not necessarily irregular grid, but the grid is constant. So we are not assuming the grid to change with time, which is a common scenario, but we are not doing it in this world. And then for the grid at each time, we have certain measurements, noisy measurements. And based on that, we are interested in learning the dynamics of the system. So dynamics of this PDE from the data. So when I say dynamics of the PDE, I mean that, so you can think of the initial condition as uncertain. You are training based on certain realization or samples drawn from this uncertain distribution, and then it should generalize to new samples or unseen samples from that distribution. So that is what I refer to by when I say learning the dynamics of the system, learning the solution from the data set D. So that is kind of what we are trying to do. So I said three components. First is the FNN. I think in my last talk at Crunch, I used this slide, so I'm reusing it. But you don't need to go through all of this. Just focus on this part. So in a FNN or in a conventional neural network, this is what we have. We have an activation function, and then weights and biases are constant, and that is an important point. And basically, then the nonlinear activation function operates on the linear transformation of W transpose X. I mean, of X basically. So this is how what a feed-forward neural network is. In essence, it is nothing but a composite input-output mapping, composite and nonlinear input-output mapping. Now, I told you to focus on this part. The reason is next I'm going to talk about attention, and attention in a normal graph, not in a normal network, and that is where it will change. So on the left-hand side, I have shown an unit of feed-forward neural network. I have assumed the bias to be 0, and if I do that, this is how it looks, where the weights are constant. The idea in attention is that weights are not constant. Instead, the weights are now represented as a function G, and it is a function of the input H itself, and alpha is the parameter of this function. So in essence, you can think of this G as some neural network, as another neural network, or it can be some other function as well. And alpha are the parameters of that neural network. So what it allows, what this kind of representation allows is basically it allows you to give or change the weights based on the input H. If your weights are, so basically you are paying attention to your input. So your weights are getting adjusted based on the inputs, and that's why the name attention, because it is paying separate attention to the input. So the weights depend on the input. So that's how the name attention came into picture. And this was for a conventional feed-forward kind of neural network. In graph, the scenario is little different in the usual case. So if you think of a graph, this is how the unit will look like. So look at the summation. The summation is over Ni, where Ni means the neighboring nodes of the ith, the neighboring nodes or the neighbors of the ith nodes. And then you see this alpha ij. This alpha ij is the attention coefficient. Hj is your input or input feature, and hi is your output feature. Okay, so this is a simple attention. There can be multi-head attention as well, although we don't use it, but this is quite common in transformers, which is a modern kind of network. That is where multi-head attention is used. And here the idea is that you concatenate, you use several attention and then you concatenate the features that you are obtaining. The point here is, or the important point here is alpha ij, which is the attention, which is the additional term, and how do you compute it? So conventionally, and this is not what we are doing, this is what is done conventionally. What we do is for alpha ij depends on eij, and eij is represented in this form, where A, you can think of a single layer neural network. For example, in our case, A is a leaky ReLU function. So basically what is happening here? What is happening in this 4 equation? It's, I mean, intuition wise. So what is happening is very simple actually. EIJ is basically trying to compute the importance of node J with respect to node I. So this is kind of computing the importance. And similarly, if you change J, it will compute importance with respect to some other J. And then that importance is being normalized here by using the softmax function, so that there is a uniformity, not uniformity in the distribution of the weights, but I mean everything is between 0 and 1, so something like that. Okay, so this attention mechanism basically in case of graph allows you to pay separate attention or importance to different neighboring nodes. So for the ith node, which neighboring node is more important, which neighboring node is less important. In some sense, it is allowing us to do that. So now coming to the proposed framework, what exactly are we trying to do, how we are trying to do, and how these 3 components, graph, attention, and feed-forward neural network is coming into picture in the proposed GrADE. So this is the autonomous system that I showed earlier while talking about the problem statement, and we are interested in solving it. So what we do is this function f, we first of all replace it by a neural network. You can think of it as that, replace it by a neural network, okay, and which is parameterized by the parameter theta. So that is kind of step 1. And then what you do is you can always write it in this form, simple, basically write it based on previous time step and then integrate between the previous and current time step. And but this integral you cannot solve it. So what we do is we use different numerical schemes. For example, you can approximate it using the Euler scheme, and if you do that, you will get the neural ODE. That is how neural ODE was developed, where this was approximated using Euler's. And so sorry, you will get the ResNet actually. Neural ODE was an improvement over that. In our case, what we do is we use the 4th order RK method, the 3/8 scheme, and if you do that, this can be represented as shown here. So if you look into the diagram on the left, bottom left, so here is your UI, your response at the current step, and then this magenta boxes are the Y1, Y2, Y3, Y4, and then you have your UI plus 1, which is the response at the next step. And yeah, and so the question is with this setup is how to represent this neural network now, how to represent there are gradients involved, which is unknown, so what to do with them, and I mean in essence how to model these magenta boxes. That is what we are looking at once you have used the RK4 scheme. Now this method is not limited to RK4 scheme. You can use some higher order schemes as well, or even some lower order schemes as well. I mean, we have used RK4 because we found it suitable for the problems that we were trying to solve. So the idea is to model those magenta boxes using graph neural network. So first of all, so now the customization is coming into picture. So first of all, what we do is we consider the network consisting of n graph network layers. So what is this n? So n is equal to the number of the highest order of the spatial derivative. For example, if I go to the previous slide, in this case, the highest order was the second order, right? UXX. So that means I will use my n is equal to 2. So I will use 2 graph network layers. If it was 3, I would have used 3. So this is kind of something which has to be customized. And then the second thing is that what should be considered as neighbor? Is it the nearest how many points? Is it the, we can one option is to consider a radius and everything inside that can be your neighbor. The other option is you can consider the nearest, say n nearest nodes as your neighbor. So in our case, what we do is we do the following. If we are solving 1D problem, as shown in figure A and B, we consider the 4 nearest nodes as neighbor. So here is a structured grid, here is an unstructured grid, just to show that it may not be equally distributed. And in case of 2D, we considered the 8 nearest node as neighbor. Now, why did we came up with this number? Well, no specific reason. The idea, we have to balance this out, right? As you increase the number of neighbors, your accuracy increases, but so does the computational cost. As you reduces it, so the computational cost becomes very affordable. I mean, it is very efficient, but the accuracy may be compromised. So we tried with, I mean, we wanted to take the minimum, to be very honest. So we tried with 2 and 4, but that was not giving good enough results. So based on trial and error, we came up with this number. Obviously, this can change from problem to problem. So that is again an open problem, right? So this is how the graph architecture is defined. So what is the advantage of this architecture, or in general graph architecture? The first thing is, since you are operating on the neighbors, the number of parameters reduces significantly. And secondly, what we do here is that we satisfy the boundary conditions. So there will be boundary conditions, right? By altering the graph nodes, the connections between the graph nodes. So for example, in our case, there was periodic boundary. So what we did was the boundary nodes were connected with both the local neighbors and the nodes on the opposite side of the domain. So u at x equal to 0 is equal to u at x equal to L, so something like that. And we connected it. We did not solve any Dirichlet boundary, but if we were solving, what we could have done is we could have removed the edges going towards the boundary, and then we could have fixed the boundary values. I mean, the boundary. So basically, we will stop update of the boundary nodes. That is what we can do. So this is what we can do. So now, going back to the architecture design, what we have discussed till now is, what are my neighboring nodes? We have discussed that. And the other thing we have discussed is how many graph network layer will be there. So these 2 things we have discussed. What
so
we are yet.
A clarifying question?
Yeah, sure.
So are you assuming that your nodes are like embedded in space and quasi-uniform? So when you say you grab like 4 nodes, for example, right? That assumes your nodes have been placed in a certain way.
No, not really. I mean, what we did was we generated unstructured grid, and then whatever was neighboring, we considered it. So
you start with like a finite element grid.
Yeah, right.
Okay, thank you.
Okay. Okay. So what is remaining is now that what is the input to the network and how is attention coming into picture. So these are the things. So there are 2 levels of design, because I am talking about, for the sake of discussion, I'm talking about a PDE where the maximum order is 2. So naturally, there will be 2 levels. So first, let us start with level 1. The input is the distance between the neighbors. So if xi, the coordinate is xi, xj is xj, so it is xi minus xj, the distance between the 2 nodes, or the norm. So the relative difference of the spatial coordinate, that is my input to a feed-forward neural network. And the output of the feed-forward neural network is gamma, which are my attention weights. Now again, the number of attention weights is depends on the problem you are solving. So if you're solving a 1D problem, for example, in case of 2D problem, this neural network will have 4 outputs. In case of 1D, it will have only 1 output. So the idea is these are attention weights, and the utility of this number 1 and 4 will become clear as I move forward. This has some specific functions, or we want it to serve some specific functions. And as I said, NN1 is feed forward neural network, right? So now next step, which is level 2, is GammaIJ was my input, was my output from the feed forward neural network, which was like my attention. And what we do is we do a Hadamard product, so basically element wise product of GammaIJ and delta Uij, and do it for all the neighboring nodes, and we take the average. So H GammaIJ delta Uij, so the operation is basically element wise multiplication, and this is how we arrange it so that the multiplication is possible. Remember, these are dependent on the neural network parameters which are unknown at this stage. And if you combine these two, the output here, so I have shown here is it to be the gradient, but it is not your gradient. What we are the hypothesis here is, once trained, this should give me the gradient. But right now, with some arbitrary weights and biases, this is not your gradient, but we want it to be the gradient, and that's why we are giving it. Although we don't have any gradient data available to us, we'll train only based on U. So this is level 1. Level 2 will be same, but we'll be operating with grad of U as my input now. So in level 2, as you can see, first of all, it is same. So there is another neural network. Again, there are 8 coefficients because second order, so that's why the inputs is the same, and there are additional parameters here, which are the theta parameters. And then you take these betas which you are getting, which are your attention weights, multiply it with the difference in your gradient, or the difference in the output from your layer 1. So this output you are getting for each node, so from there you can compute the difference, and that is what you have here, and then you multiply them element wise again. And again, I've written here H because I expect it to be the second order derivative, the spatial derivative of U, second order. But at this stage, it is not. I mean, we are expecting it to be the second order derivative once trained. And so, yeah, so this is the second graph layer. So now I have this second graph, this GN2. I had this GN1. So these two things, and then I have my U also at the current step, which is known to me. All these three are now provided as input to a neural network, a feed forward neural network. And it has again additional parameters theta n3. And the output is Y. The output is Y. So now this is my Y. So given some U, you can, and X, you can, at some given T, you can compute, I mean, you can find this out assuming theta is known, which is not at this stage. And that will give you the Y. And now you have the usual framework that I showed before. So basically this one. So basically now each of this Y is modeled using what is shown here. And then you, from UI, using this thing, you can go to UI plus 1. And given that you have observations, it is a data driven, so you can train it simultaneously for all these parameters. And as I said, the hope is that once trained, this first graph network should give you the gradient, the first gradient, the spatial derivative, and the second graph network should give you the second spatial derivative. Okay, and we'll see, we'll verify it, that whether it is giving it, whether we are getting it or not. So that is basically the overall architecture. The overall, so this is the overall architecture, how it looks. For training, we can use message passing. And interestingly, this is the expression I showed earlier. And this is like the message passing step. So in message passing step, first is you aggregate information from the neighboring nodes. So H is like aggregating information from the neighboring nodes. And then you update it when you sum it, and that is your update of the ith node. So this is basically your message. This is also acting as your message passing equation. But this is a complex network, right? There are 3 or 4 networks, I mean, we're talking about. And so you have to be extremely careful during training. So for example, learning rate we reduce it slowly as you go. As epoch increases, the learning rate decreases, and we use a list for that. Also for the initial epoch, and I will show some results for this also. We roll out the temporal rollout. We explore fewer time steps for the initial epochs, and then as we proceed further, we explore the more number of time steps, with the idea that it has some idea about the dynamics already by exploring the fewer number of time steps that it has been trained on. So this is also something we do, and this helps in not only in computational accuracy but also in efficiency. And I will show you one case study where what happens when you do this and what happens when you don't do this. So all this thing was done using PyTorch, and we used for the differential equation part, we use the library torch diff eq, and so using this you can use those RK4 schemes and all those things, compute gradient and all those things in an efficient manner. So that is what we used here. So this is the overall algorithm. So you can see that the number of time steps is a function of epoch, and also the learning rate is a function of epoch. So that is what I was talking about a little while ago. And then the rest of the thing is kind of same. The message passing is there inside this, which is not shown here explicitly, Back propagation is a challenge. We do it using adjoint method. So basically, we compute the gradient using adjoint method for the gradient. So we solved the Burger's equation in 1D and in 2D. So the equation is well defined. So I will not go through the equation. So I will define the rest of the problem statement. So the boundary condition is periodic boundary condition.
Excuse me?
Yeah, go ahead.
This is Lulu. Could we go back to the previous slide?
Yeah, definitely.
So for back propagation, why do we need a drawing method? I think this can be directed down in PyTorch, right?
Yeah, it can, but there is a graph and then the neural OD is there, right? So it is more efficient. It is more efficient. That's
okay, for efficient. Yeah, but it's doable directly, naively.
Yeah. It is doable. It is doable. Yeah.
Okay, thank you.
Yeah. So coming to the boundary conditions, it is periodic boundary condition. Initial condition is generated from a Fourier kind of Fourier expansion, and we have taken 4 terms here. AL, BL, and C here are are random. So basically, this is like a random bound initial condition. A and B are drawn from the Gaussian, and C is drawn from the uniform. The spatial domain is discretized into 512 points in this case, non-uniformly. And the time step is for generating data, the time step is 0.001. So that is for generating the data. Coming to the architecture, so there are 3 FNN, right? One for the GN1, one for GN2, the 2 graph attention, and one for the overall, where you give U, GrADE, and everything as an input. So for all the 3 FNNs, we have considered shallow networks, so only a single hidden layer with 32 neurons. Activation, we have used like leaky ReLU throughout with alpha is equal to 0.2. For training, we have 120 samples of the initial conditions, so from that Fourier series, and we have data at 4 time steps. In this case, initially we are not changing the learning rate, so the learning rate is 0.007, although we change it later, and the training was run for 201 epoch. Okay, so here are the results. So these are 2 initial conditions which were not in the training set, so like test data set, you can say. The first row corresponds to the true solution obtained using Phoenix. The second row corresponds to the prediction of the network, and then there is the L1 error that you see, and you will see that it is doing a reasonably good job in capturing the evaluation of this in capturing the dynamics of the system. One important point here to note, remember that here we are using a larger time step, point number 1, and we have 4 time steps, and these are uniformly like 0.007, 0.014, and so on and so forth. So in essence, we have data up to 0.028. That is what we have. And you see the y-axis is the time, and we are predicting up to 0.2. So it is not only learning in the training range, but it is actually learning the dynamics and extrapolating to the future significantly.
So I can ask a question. So you had a comment about that this is training on a different initial, or you're doing a test on a different initial condition. Can you share specifically what that initial condition is, and in what sense it's out of distribution from the training set?
Correct. So it is from the same distribution, but different random numbers, right? So this is my initial condition. Here AL, BL, and C are my random parameters. So you draw 120 samples, those 120 are my training. You draw 2 additional samples, and which are different from those 120, those are your test set. Actually, we had done it for 30, but yeah.
So it's in distribution, but a different sample.
Exactly. It's not out of distribution. No, it's not out of distribution. We have not tested that.
Thank you.
Okay. Yeah. So these are the results, and it matches quite well for this case. So then we carried out different case studies actually. So LIT is last training. So this means I am using 2 snapshots, and then 3, and then 4 and 5. So last training index, last time integration time actually. And then these are the different setups for this, and some number of epochs, and the training scenarios is same. So this is variation with when you change this 2, 3, 4, 5, how it changes. And in this case, we change the number of initial training samples. So for the training samples, you see that as you increase from 30 to 120, the result improves as expected. Yeah, the green and you can say that 60 and 90 are almost same. So there is no such much difference between 60 and 90, but from 30 to 120, there is a significant improvement. However, for these 4 cases where you use the last time integration to be 2, 3, 4, and 5, that means we see that that the results are almost same. For 5, it is deviating after certain time index, and we think that is overfitting. It is overfitting the data because the training loss was less, but yeah, but overall the result is there is no significant difference. Obviously, when you increase this, the training time increases significantly. So it is obviously suggested you use less number of last time integration. So the lower the better, without a doubt. And then coming to the derivative part. So we hypothesize, our hypothesis was that it should learn the gradients, right? So U is, so this is not of importance. This is not of importance at this stage. This is the first derivative, and this is the second derivative, actual from Phoenix. And then these are the predictions, and you can see that there is a good match actually. So basically, this is the output of the GN1, the first graph layer, and this is the output of the second graph layer, and it matches quite well. The second problem is again the Burger's equation, same kind of setup, but yeah, more challenging because 2D now. Okay. Now, here, okay, here is a typo. We have used 64 by 64 grid initially, but then we use the same sample points but generated it randomly over the domain. So the results I'm going to show is for the random one. I did not put the regular grid results, although it was obviously better. It was giving better result for regular grid without a doubt. For data generation, in this case, we have used a time step of 0.005 in Phoenix. And okay, some sample of the initial condition is shown here. I did not show it. So these are like some initial conditions randomly generated from this Fourier series. And then, yeah. So these are the random initial conditions for the x and y velocity components using the truncated Fourier series. Training. So in this case, for the GN1 and GN2, the two shallow networks, we use 32 neurons as before. But for the final neural network, we use 64 neurons, again determined based on trial and error. In this case, we have less number of training samples, so 90 training samples of the initial conditions as before. Previously, it was 120, and we have snapshot at 3 time steps. The activation function is same. The delta t is 0.02, and which is significantly more than the 0.005, which is used in Phoenix. Hyperparameter setting. Okay, in this case, the initial learning rate is this one. It will change to 0.054, and as the epoch proceeds, and the number of epoch is 201. And here are the results, again, two different initial condition test set. Again, you can see that we are predict. So the first row again is the true solution. By true, I mean finite element solution. The second row is the solution obtained from the proposed approach, and then there is the L1 error. And again, it is doing reasonably good result. Yeah, in some locations the error is little bit high, I will say, the yellow ones, but overall I will say that it is doing a reasonably good job in predicting the solution, the dynamics. And again, it is significantly it is extrapolating significantly in time as compared to the training part. So this was snapshots, right? This was at certain x and certain t, right? Okay, sorry, one mistake. This was at certain t. This was x and y at certain t. This is the time evaluation. So we are going up to t equal to 0.5, and yeah, and these are the evaluation. So again, the first row is basically your true solution. Second row is the prediction, and then the L1 error. As expected, as you go ahead, the first column is kind of useless. That is the initial condition. But as you go ahead, you see the error is kind of increasing as expected. It is supposed to increase as you go ahead in time. But nonetheless, the pattern and the is captured nicely, both for U and for V. So the first 3 corresponds to U, and the second 3 corresponds to V, so the 2 components. Again, the same case study, the last integration time, and in this case, 3 is giving better result. 3 is giving better result. In the previous case, all were giving kind of equal result with little overfitting in 5. In this case, 2 and 4 are giving better results, and not better result. 3 is giving the best result. So this is one point. Actually, we spent some time here to understand what is happening. So it's not like, ideally, as you increase lit, your results would improve. That is the ideal scenario, right? But what is happening here is that initially it is improving, but then as the network is becoming more as the loss function is becoming more complex, not the network, the results are deviating. So there is an optimal, and at this point, we have determined the optimal number of lit by trial and error, but this needs to be formalized somehow. How to determine this optimal lit is a open problem at this stage. And coming to now the adaptive rollout time, that in the initial epoch you only train for certain lit, and then you increase the lit as you go ahead. So that is the case 2 here, and case 1 is when you keep it same. Okay, and you can see here that so we have shown both error and time elapsed, right? So in the initial epoch, as you are only going up less number of lit, actually the error is kind of more. But then as you proceed through the epochs, you start going or learning the long-term dynamics or long-term dependencies, and the error goes down. So that is what is happening in this case. As for time elapsed, also you can see that the time required for this thing, I mean, for the proposed approach is significantly less as compared to the other approach, right? As compared to the other approach, where you keep the late constant. So we are using FNN for the attention, right? But that FNN is not the only option. You can use Taylor. There is another algorithm that can be used, which is TaylorNet, where they use Taylor series for the attention. So we compared with that to see how it performs, and it seems that the proposed approach performs better as compared to the TaylorNet one, which is already there in the literature. And coming to the gradient, so these are the first derivatives and the second derivatives. In this case, the overall pattern is been captured, but there are some places where you will find some mismatch. So one is, for example, here I can see. So this is not exactly matching with this, but overall the pattern is kind of being captured. So the graph is capturing the gradients, both the first and the second. So coming to the conclusion, so that was all actually. So we found that overall the performance of the GrADE is found to be good. This is primarily data driven. I mean, although it is learning the gradient and the graph is having some information about the physics based on the boundary and all those things, but it is primarily data driven in nature. And this was, I mean, and there is significant more. I mean, significant improvement can be made over this. For example, can we make it physics informed? I mean, if we are learning the gradients, can we use those things and train it in a physics informed manner? That is an obvious way, and we are trying to explore it at this point. This is a more challenging problem. What if the grid is not same for different time? If the grid is changing with time, so what to do in that case? So dynamic meshing, adaptive time stepping is kind of easier. And then lastly, in this case, I said that the number of graph layer is dependent on the highest order of the spatial derivative, which means I have prior information about the governing equation. But there are many problems, specifically in biology, where the governing equation is not known. All I have is data. And in that case, I don't know what is the equation, so I don't know what is the highest order, and so on and so forth. So how can we automate the graph architecture, which currently is to be customized manually? So that is, I mean, this is, I don't even know how to do it. I have no idea actually, but I mean, this will be an important step we can do if we can do it, the last one actually, because then it can be used for black box kind of system with no information about the physics at all. Lastly, I would like to acknowledge, yes, actually, so he's an undergrad student, third year, so BTech basically, he's doing his bachelor's right now, and he's the one who actually did most of this work. So he started working around January this year, and he is the one who actually did most of the work. So most of the credit should go to him. I was just guiding him actually, and obviously there are funding agencies. Yeah. So with that, I will stop. Thank you, and I will be happy to answer any questions.
Thank you, Souvik.
Yeah.
Can I ask a question? Hello.
Yes.
Yeah. Okay. Yeah. Thank you so much. Very beautiful talk. Nice. Very beautiful results. I have a question on the first example. If you don't mind, can you show?
Yes. Certainly. Sorry, I stopped it.
Yeah. Thank you so much.
Okay. First example, right?
Yeah. First example. So basically, like you use 3 time steps to extrapolate for a really long time, as far as I can remember.
Yeah. So this one, right?
Yeah. Right. Yeah. Sorry, maybe you already mentioned that, but I didn't catch that. So on your training data set, how long of the time do you have? How many time instance do you have? Is that also like 4 time steps for each sample?
For training, yeah, it is 4. So that means I have data is at 0.007, 0.014, 0.021, and 0.028.
I see, I see. So is the example you are showing here in the training data set, like, I mean, with the same initial condition as one of the training data set, or is it?
No, this is a different one, but from the same distribution. So this is the distribution. So this is a different one. This was not in the training, but from the same distribution. Distribution is same.
I see, I see. Yeah, so that means like you have only like say 3 steps, time steps, and then you can extrapolate to like very, very long time, right? So what is the key here that make the extrapolation so stable and that can be
Yes.
such
So
a long time?
yes. So I think this is the key. I mean, this is the it is kind of learning, not learning the data mapping. It is learning the time integration scheme itself. So because this is the RK4 scheme, right? And so it is learning the time integration scheme itself. And if you learn the time integration scheme, the idea is in that case, you can actually extrapolate. If you're only learning a mapping, then you can't, right?
Okay, I see. So does that mean like when you generate the data, you are using the RK4 too, or not really? You are not using RK4?
For generating data, we are not using RK. We are using Phoenix, and I forgot the exact time stepping we are using, but we are not using RK. That I can say.
I see. So have you ever? Yeah, sorry, I have maybe too many questions.
Yeah, no, that's fine.
Yeah, have you ever checked maybe the parameters in your neural network here? Does that match the parameter in RK4?
No, we did not. That is an interesting point. We did not actually. We did not track the parameters. It will not be the parameters. It will be the output of the neural network that is to be tracked actually, because Y1, Y2. No, actually we did not. What we tracked is the gradients, and that was matching, but we never tracked the. Yeah, I should do it. Yeah, that's a nice suggestion.
Oh, I see. Yeah. Thank you so much. That's very nice results. Thank you.
Yeah.
Ask a question?
Yeah, certainly. Yeah.
So my name is Nat Trask. I'm at Sandia National Lab. So there's a few words. So essentially what you're trying to do is learn a finite difference stencil, a nonlinear finite difference stencil, and then embed that in a neural ODE. So there's a few works that have done something similar. For example, like convolutional neural networks, you could do that on a Cartesian grid. For this way of doing it, I'm just trying to understand the architecture. For this way of doing it, you don't get to take advantage of any weight sharing, right? Like you have from scratch a different stencil as you go from node to node in the mesh.
Yeah, so there is node sharing actually. So for example, so this neural network, where is that neural? Let me go back. So this attention networks, right? So for example, let us say this network, right? So this network and this parameter is not changing from point to point. So this is same for all the nodes, this network.
Oh, okay. Well, so yeah, so this is this was the core of my question. So I was hoping you could share, it seems that the main contribution is this attention way of learning the stencil. Can you share your design strategy or what this is meant to do, or is it a question of you set everything up on a graph, you want to learn a stencil, and then you just
correct
swap blocks in until it starts working? Or
yeah, you actually you actually answered the question itself. Yeah, the idea is, so there are 4, right, these things, and then I am multiplying it with the difference in u. So basically, if you think about the finite difference, you are right. This is like ui minus uj, and then it is the gamma is supposed to learn the weight. So it is like it should learn the finite difference stencil in some way. And so that is the idea. So now, since that is why there is 4, right? The number 4 is coming from that fact, that finite difference you are saying. And similarly, the same reason there is 8. So that is what is coming from there. Other things, we are not forcing anything. The idea is that it should learn on its own.
And so so you had this comment that in order to handle high order differential operators, you had to go to depth, which runs contrary to the intuition that this is learning a finite difference stencil. So usually you would go for a wider finite difference stencil in order to, like with the traditional finite difference method. And Lars Rutoto has also done some work on this, using
Yeah.
finite difference stencils as an input to a neural network, as like a feature embedding or whatever you want to call it. So
Yeah,
can you comment why does it not work when you go to wider? I would expect to go to more neighbors, not to depth, to handle high order operators. Did you do those experiments?
Yes. So what is happening is this beta, right? This beta, when you multiply, you are supposed to get the second order gradients, right? So if you have a third order, say third order in you will need one more graph layer. So each graph layer in our design is learning one gradient, like one order of gradient. So if one graph layer, it is only learning the del u by del x or grad of u. If there is two graph layers, the second one is actually learning the Hessian. So that is the design.
So it's designed to learn high order derivatives as the composition of first order derivatives?
Right.
Is that the way?
Exactly. Yeah, exactly.
Okay. A very, very nice talk. Thank you.
Okay, thank you.
Maybe we could wait for Professor Kanyarakis' comments.
So that I'm okay. I don't have any questions.
Okay. Are there more questions for Souvik? So if there are no questions, thank you, Souvik. It was a wonderful presentation. Thanks a lot. Okay.
Yeah.
We could move on to our next speaker.
So thank you. I will take your leave. Okay.
Thank you.
Because it's night here. Okay.
Good night.
Good night.
You can see the slides changing, right?
Yes, I can. Yeah.
Perfect.
Okay. So our next talk is basically a joint talk by Saad, Qadeer, and Brek, Meuris. And they would be presenting on the topic, a spectral approach for time-dependent PDEs using machine-learned basis functions. A quick introduction to both of them. So Saad Qadeer is a postdoctoral research associate at the Pacific Northwest National Laboratory, working on multiscale modeling and high-order numerical methods. Prior to joining PNNL, he was a postdoc at the University of North Carolina, Chapel Hill, working with Boyce Griffith and Greg Forrest. He obtained his PhD from the University of California, Berkeley, under the supervision of John Wilkening, and did his undergraduate work at the Lahore University of Management Sciences, Pakistan. Brek Meuris, who is the second speaker of the talk, he is a PhD student in the Department of Mechanical Engineering at the University of Washington. He obtained a Bachelor of Science and a Meng from the University of Louisville. His research interests include model reduction techniques, multi-scale modeling, and machine learning. You have already shared your screen, Brek, so you can start off with your presentation. Thank you.
All right, thank you very much, Somdata. So as was mentioned, this is going to be a talk in two parts. I'll take care of the first bit, and then Brek will contribute the second part. So our starting point is going to be the universal approximation theorem, which naturally leads to the deep O-net framework. And what the universal approximation theorem briefly states is that if you have a continuous operator on certain spaces, then that operator can be approximated very well by a shallow network. The theorem itself doesn't tell us much about what the parameters of this network are going to look like, but it does give us a brief setup, what the architecture is going to be. So generally, it ends up looking like a part, the branch net, which depends on the function u itself, and then a trunk net, which depends on the spatial parameter, the spatial variable y. And the key insight of the DeepONet framework is to make this computationally feasible by replacing these shallow nets by deeper nets. Once we have a deep architecture like this, then it is to be hoped that these operators can be mimicked computationally much better. So we can go ahead and test that. In the first part, I'm going to restrict myself to mainly this toy problem, the periodic advection problem. The more complicated numerical tests will be handled by Brek. So in this case, we are going to take G to be the solution mapping, which takes the input, the initial condition to the final solution at any point in 0, 1, and this is trained for time values that go from 0 to 1. These are the various parameters over here. The activation function that we're using over here is tanh, although we will have a comment to make about that later on. So as I said, the training takes place for t going from 0 to 1. And if we go ahead and test that as the number of epochs is increased, we can see that the errors as t goes from 0 to 1 are very nice. Generally, they stay around 0.5%, which is fantastic for this particular initial condition. So we can conclude from that that DeepONet works like a charm inside this domain of training. However, just for the sake of it, what if we were to push this? So if you were to stretch DeepONet and try to extrapolate the solutions beyond t equal to 1, just evaluating them outside the training interval, we can see that the errors end up growing. Now, that's not an indictment on DeepONet. It works as advertised over here. It's just that raises the question, is there a way that we can harness the DeepONet machinery to extrapolate the solutions beyond the training interval? And a couple of observations. The first key insight is that the solutions that a DeepONet spits out are going to be linear combinations of these trunknet functions, and that, assuming that the DeepONet has been adequately trained, these can be computed regardless of how weird the spatial domain is. And as we saw earlier, these solutions are very accurate inside the training interval. So what that suggests is that if we were to just freeze these trunknet functions at some time value, then they would just depend on the spatial variables. And as a result of that, because of their good representational capability, they might be useful in a spectral procedure. So that's the main idea that we are going to be proceeding with. Now, a couple of issues need to be addressed before we proceed. Firstly, what particular value should the trunknet functions be frozen at? So again, going back to our old friend, the periodic advection problem, here what you can see are the trunknet functions on 0, 1 moving with time. Let me play that again. So as you can see, in the beginning, there's a lot of spatial variation in the first few trunknet functions. But as t goes on, and particularly the further and further away it gets from the training interval, these functions end up becoming more or less constant. And that indicates to us that we should take the time value at which these trunknet functions are frozen to be as small as possible. So we are going to take t equal to 0. Another thing that we can do is we can just sample these trunknet functions at t equal to 0, 0.1, 0.2, and so on all the way till 1, so remaining inside the training interval. The more, the merrier, really. But in the results that we're going to report today, we are just going to stick to t equal to 0 because that doesn't really affect the procedure that we are going to be sketching out. And just one brief comment. So the way we are going to be obtaining these functions for use in the spectral method, we are getting these, we are getting a linear space kind of for free because of the DeepONet setup. This has to be contrasted, for example, with the Galerkin neural net setup that Mark Ainsworth introduced recently, in which the functions that are being used in the Galerkin procedure are assembled iteratively. All right, so before we go ahead and plug these functions into a spectral method, there are a few things that we need. First of all, we need to find a hierarchical orthonormal basis, which we're going to call U sub L. So again, a few comments about those. When we talk about a basis, we actually want the functions rather than just evaluating it, or rather than just evaluations of those functions at a few points. In the ideal case, we would like a change of basis formulation, change of basis formula between the orthonormal functions and the truncate functions. When we talk about orthonormality, that means obviously in the sense of computations, in the sense of numerics, so just with respect to some high order quadrature rule. And finally, the hierarchical bit. So this has to be seen somewhat in the sense of, so what we are aiming to do is get a hierarchical basis in the sense of Fourier or orthogonal polynomials, so that the functions are ordered either by some notion of frequency, the number of zeros, how much they oscillate. And in the ideal scenario, we would like the coefficients of smooth functions. So if you were to expand a smooth function in terms of such a basis, then we would like those coefficients to decay rapidly, as for example happens famously with Legendre polynomials or Fourier functions, etc. And the key reason we really need a hierarchy over here is because an overarching goal of this approach is to use these functions in a reduced order modeling method, and the presence of a hierarchy would help in being able to identify the resolved and the unresolved scales. So again, Brek will take care of that in a moment. So let's turn to the numerics of this. When we talk about orthonormalizing a given set of functions, the first thing that comes into your mind is obviously Gram-Schmidt. So in this case, let's just take this to be a high order quadrature rule, evaluate the truncate functions at these points. Let's take W to be the quadrature weight diagonal matrix. And we can run a Gram-Schmidt process with this, which is essentially just the QR decomposition. Now, the R matrix that we're going to get from this QR decomposition is just going to be the change of basis matrix. So that seems pretty straightforward. However, there are a couple of issues with this. So you see, the Gram-Schmidt algorithm depends on the initial ordering of the tau subcase. And because it's dependent on how these functions are ordered in the first place, it may not yield the desired hierarchy. So just to give you a toy example, let's say we start out from Chebyshev polynomials, just the first 9 Chebyshev polynomials ordered T0, T1, and so on. And if we were to run Gram-Schmidt on those, well, we would end up with orthogonal polynomials on -1 to 1 in the sense of without weight. So we end up with Legendre polynomials. However, if we were to just flip their orders, then in that case, the first function that we end up obtaining has 8 zeros, the next one has 7, and so on. So this is just to illustrate that illustrate the sensitivity of the Gram-Schmidt process to the initial ordering of the functions, and why we need to figure out another method that does not depend, or which is not as sensitive to the initial ordering. So what we're going to do is we're going to get some inspiration from principal component analysis. Basically, what we're going to do is use the truncate functions and build their covariance operator. Now, it's a pretty famous result that their eigenfunctions arranged in order of decreasing eigenvalues form the principal components. Now, just to give you a little bit of intuition into what we mean exactly by this, let's say I were to take the first R of these eigenfunctions, take their span, and as a result of that, the R-dimensional subspace that we get from that has the property that the orthogonal distances of every one of these input functions, so to speak, the sum of the squares of those distances is minimized by this particular R-dimensional subspace compared to any other R-dimensional subspace. For example, if you imagine these tau sub k's as just various points scattered about, then the first principal component is going to help us set up this one-dimensional subspace such that not the least squares, not the vertical distances are to be minimized over here, but actually the orthogonal distances or the sum of the squares of the orthogonal distances will be minimized. And this is what we are going to try and do at each step. We are going to try and find progressively more, and we are going to assemble the principal components of the covariance operator or of this data set, and that will help us find the orthonormal eigenfunctions. So the pros of this, well, it is independent of how the tau k's are initially ordered. Because of the properties of the principal components, these are going to eventually end up progressively covering S with the largest variation accounted for at each step. And finally, this also provides us with a pretty useful way of identifying the actual dimension of the trunk net space, so that if it turns out that an eigenvalue is too small, we can play around with this threshold. Then it turns out that the corresponding eigenfunction is merely noise. So let's go ahead and look at how we would set this up, the actual numerics of this, how we would actually compute with this. The first thing that we can do naively is set up the covariance operator, or at least discretization of it, and perform its SVD or eigen decomposition. But that turns out to be prohibitive because in this case, it's going to be an n sub q by n sub q matrix, and the number of quadrature points are going to scale with dimension. So that's definitely not a route that we want to go down. Alternatively, what we can do is we can simply define what's called the reconstruction operator for these trunknet functions and look at a couple of its properties. So first of all, it's pretty easy to work out its adjoint. It's just going to be the inner product, it's just going to be the result of the inner products of any function g with respect to these trunknet functions assembled in a column, so a p-tuple. And likewise, we can write down its SVD in this form. So this is just a finite rank operator, so we can easily work that out. Now, if we were to combine the SVD and the adjoint, it's first of all pretty easy to work out that the covariance operator is just A composed with the adjoint of A. And plugging in the SVD for both A and A adjoint, it helps us work out that the SVD of the covariance operator is going to be in this format, so that just looking, so that tells us why the SVD of the covariance operator is going to yield the orthonormal eigenfunctions, because they show up very naturally in this SVD form. However, if we were to instead work out what A adjoint A is, that yields us, again, that provides us with the singular values along with the p-tuples v sub k's assembled in this manner. Now, why is that important? It turns out that just from v sub k's and the singular values, there's a very easy way to recover the orthonormal eigenfunctions. And you'll notice that this is a relationship. This provides a linear relationship that allows us to flip back and forth between the u sub l's and the tau sub k's exactly as we want it. And it only needs the v's and the singular values. So this can be pretty easily found by just computing the SVD of the discretization D A star WA. And this is a P by P matrix. We remember P is just the number of trunknet functions that we started out with. So this is great. This is computationally feasible. However, just one word of caution. If we were to actually set up the matrix D and perform its SVD, we would end up computing the squares of the singular values. Yeah. And if we end up taking the square roots, we would only be able to get them to an accuracy of 10 to the negative 8 if you were doing this in double precision. So it's probably better to set up the matrix square root of W times A. So we at no point end up computing the squares of the singular values, with the result that the SVD phi SV star, we can just throw out the phi and make use of the S and the V matrix. All right, so let's go ahead and test this approach on our old friend, the periodic advection problem. And the first thing that we can do is we can just use the ReLU activate. So we can use the trunknet functions that are obtained from a depot net trained with the ReLU activation functions. And what we can see is that the first few basis functions, well, they're pretty rough, as you would expect using ReLU, pretty bumpy. The singular values do decay, not rapidly. But for example, if we go ahead and expand e to the sine of 2 pi x and look at the expansion coefficients, they don't decay rapidly. In fact, they just decay algebraically. They definitely don't decay exponentially over here. And we haven't shown that over here, but it turns out that these functions aren't really that accurate in the first place at all. So that's a bit of a bummer. What we can do is use a depot net trained with the tan H activation functions. And looks like we're in business because these basis functions, first of all, are very nice, very smooth. They are definitely, they appear to be ordered by the number of oscillations. So there is that. Singular values decay very rapidly, so that basically the 37th, 36th point is, well, we really are only going to need 36 to 38 functions from here, because everything after that, as I mentioned, is just going to be noise. Unfortunately, the expansion coefficients for the smooth test function start out very promisingly, but somewhere around the 27th, 28th mark, they start going back up again. And the reason for that is pretty straightforward. You see, when we computed the orthonormal eigenfunctions using this recipe, we are dividing by the singular values. So when the singular values become too small, it turns out that the round off error, epsilon over here is the machine precision, whenever the round off error ends up being larger than the result that we are, or the quantity that we are computing, the error is going to swamp that out. And as a result of that, we are going to get this V shape. And that tells us that this recipe is basically, well, it doesn't like mixing with finite precision arithmetic and such sharply decaying singular values. So we need to figure out a way that does not use this formulation, this recipe where we are dividing by the singular values. And in order to do that, we need to go back and pick up a matrix that we threw away earlier. Remember, the SVD of this matrix B was phi S V star. We made use of S and V, but we threw out the phi. But just from the matrix phi, we can work out what the values of the orthonormal eigenfunctions are going to be on the quadrature grid by hitting it on the left by the inverse of the quadrature weight square roots. So we can work out what the quadrature, we can work out what the orthonormal eigenfunctions are going to be at the quadrature grid. However, to work out their values away from the grid, we are going to project them on Legendre polynomials. So the way that's going to work is just take whatever your U sub L is, inner product with U sub J, where U sub J's are the Legendre polynomials, and append that with U sub J's. In order to work out what this inner product is, we would need a way to work out or compute this inner product or this integral. And for that, we would need these functions to be evaluated at quadrature values at the quadrature grid. And as it turns out, that's the only thing we really know about these functions accurately. So by a lucky stroke, it turns out that this projection can be carried out pretty accurately. So to sum up, from this form, it turns out that the basis functions are just going to be polynomial expansions, and the choice of these coefficients is going to be guided by debonate. Does this work? Well, let's just go ahead and work out the coefficient expansions, the coefficient of the expansion. And it turns out that these do decay all the way to 10 to the negative 11 something. In this case, we are just using r equals to 127 as the highest degree of the Legendre polynomial for the projection. So to sum up, as these eigenfunctions are smooth.
Can I ask a question? Have you
please.
plotted these polynomials? Are they what kind of polynomials are these now?
Oh, right. So for the first 6 functions, for example, they look pretty much just like this. If you go ahead and work out what they're going to be around, let's say the 30th mark, they are pretty.
So you don't, sorry, so you don't have the linear.
Linear in like, sorry, linear in what sense?
The linear, if you go back, I was just looking at the polynomials. There's no linear polynomial. Like if
no.
Right.
Oh, right. Yeah, no, there's no. So by that, like there's no constant polynomial either. No. But it's just that all of those polynomials are combining in a way to give us these various functions. So yeah, so there's no like constant, linear, quadratic, and so on.
So how do I know that I have a complete basis?
Right. At the outset, you don't. But we are going to come to that in a moment. So that's a very good question. So even though these coefficients do end up decaying rapidly, there are no guarantees as of this point about accuracy. So we are going to talk about that in a moment.
So in other words, you're going to approximate the constant and you're going to approximate the linear function, right?
Right. Yeah. Yeah. All right. So before we get on with that, just a few points about this formulation, the setup. So these functions are smooth, so the projection is going to be pretty accurate. And as a result of that, we can be pretty confident that the UL tildes, the projections, match up pretty well with the actual functions, the usables. This only relies on well-conditioned operations, basically just hitting it on the left with the inverses of the quadrature square roots, quadrature weight square roots, and the summation. So that's pretty good. And because we have a polynomial expansion, we can use fast polynomial methods for differentiation, evaluation at arbitrary points, like recurrence relations and such. And finally, as again can be seen from this diagram, and as I mentioned earlier, if we only need 37 to 38 functions, and if we can identify those functions at the outset, that tells us that we don't need to use the full coterie of 128 trunknet functions that we started out with for our spectral method. And that would lead to a significant reduction in system sizes because we can throw out any function beyond the threshold. So coming to the key point, how good are these functions at approximating generic functions? Let's just define this orthogonal projection for these eigenfunctions, for these basic functions that we found. And we want to get a handle on the gap between projection of f minus f. So one thing that we can do is just run it through some run this or compute these quantities for some sample functions. And we can see that the errors do creep up as the function becomes more and more oscillatory. So just to get a handle on this, let's work out a rudimentary upper bound. So the first thing that we can notice is that because u sub k's are orthonormal, this is an orthogonal projection on the trunknet space S. So let's also introduce the Legendre transform expansion, the Legendre projection. Remember, q sub j's are the Legendre polynomials. Now, because P composed with L sub R is still going to be a mapping on S. It's going to be an operator with S as its image, but not necessarily an orthogonal projection. That means that this is going to be larger than PF minus F norm. Use the triangle inequality to break it apart into two portions, and let's analyze these two. So first of all, the gap between the Legendre projection and the function itself. So this can be pretty easily worked out because of the completeness of Legendre polynomials. This is only going to depend on the Legendre coefficients beyond this threshold R, where this works for any R, by the way, so R is completely arbitrary. And if we choose R to be large enough, this tells us that this portion is negligible because the Legendre coefficients decay rapidly. So we don't really need to worry too much about this. Let's turn to the other part. And in this case, just opening this up explicitly, we can work this out to be this. And as you can see in here, this quantity is exactly what Professor Karniatakis was mentioning a little while back. This is going to be measuring how well can our trunknet space approximate the various Legendre polynomials. So let's go ahead and look at that. So J over here just tells you which polynomials are being approximated, etc. So the constant, linear, quadratic, all of those work pretty well. But as you can see, the more oscillatory your Legendre polynomial gets, the harder and harder it is for the trunknet space or this projector to approximate it well. Fortunately, we don't need to be fazed by this rapid growth in errors because this is going to be damped by the decay in the Legendre coefficient. This is going to be phased, this is going to be damped by that. So if we were to actually go ahead and look at the results for all three of these functions, multiplying the Legendre coefficients with these errors, it turns out that even though there is a slight increase, eventually everything ends up settling down. We can also work out what the sums of all of these quantities are going to be. And of course, they do provide an upper bound, as you would expect. But the key point at this point is that the more oscillatory the function gets, as can be seen over here, the harder it becomes for the trunknet space to approximate it in the first place. With that said,
excuse me?
Yeah, please.
Excuse me, this is Lulu. I have one question. So when we have, let's say, more oscillatory functions, so one reason I think is it due to, because when I train the dipole net, so from some training data set, if in the training data set, there's no this kind of high frequency functions, then the basis is impossible to recover this, right? Is this?
That's very true. That's very true. Yeah, that might be it. So it's just that if we were to actually like train DeepNet with more and more complicated functions, put it through its paces with really challenging functions, then of course it's going to learn, and this is going to yield much better results over here. Although another thing that I might mention at this point is that we are getting these results for trunknet functions evaluated just at 0, but if we evaluate at t equal to 0, but if we were to evaluate them at a bunch of different time values, then it turns out that these errors are much, much better behaved. So there is also that.
Oh, I see.
So
Okay,
both of
thank
those,
you.
both of those options can be explored, absolutely. Finally, all of this works great in one dimension, but in higher dimensions, there are a couple of roadblocks that we are going to run into. So the first one is, what do we do for quadrature rules that we've been so blessed with in one dimension? And secondly, we don't have necessarily an analog of Legendre expansions in high dimensions that we made use of earlier. So let's take these one by one. First of all, the quadrature rules in high dimensions, the quadrature rules can be built by just taking tensor products of one-dimensional schemes, but they won't, for example, necessarily work from scratch for a domain, for example, like this. So a couple of ways of getting around this. One way is to go ahead and perform some domain decomposition. So chop it up into different parts so that each part looks like a nice rectangle. Use local quadrature rules on all of them, and that's it, basically. That provides a nice global quadrature rule. Another option is to take our domain, embed it in a larger, more regular computational domain, figure out a quadrature rule on this larger domain, and just restrict it. Now, of course, the first scheme is going to be more accurate. The second one is much, much easier to set up because it doesn't rely on a piecemeal chopping up of the domain. However, the second domain, the second procedure does have its benefits, and that is it's easier to set up, and it also sort of suggests a way forward where the analogs of legendary expansions are concerned. Because what we can do, for example, for a domain like this is to extend the given u sub else. Remember, let's say we just know the u sub else at these isolated points in the physical domain. We can just extend those functions, u sub else, to this larger computational domain. And on this more regular domain, those functions can then be expanded in terms of products of legendary polynomials. But again, that is something that we are still exploring, and any ideas that you may have, more than welcome. All right, so this was the painful bit. Brek is now going to come in with the more interesting, the actual numerical results. So if you have any questions about any of this, I'd be happy to take them, or we can go to those at the end. And in the meantime, Brek can set up.
So, Saad, what do you do with the branch? So you just take the trunk. You don't do anything with branch, right?
We don't do anything with the branch because all of the spatial information is inside the trunknet function. So we are at this point ignoring the branch totally. Yeah.
Okay.
You can share your screen, Brek.
Okay. Yeah. Okay. Can everyone see that now?
Yes.
Rearrange a few windows here. Okay. So as Saad mentioned, I'm going to take over now and go over some of the numerical results we found using that procedure and construction that we just presented. We looked at 4 PDE test cases thus far. It's kind of an initial proof of concept with this, a few linear and a few nonlinear PDEs. So to start here, just a little bit of the background as far as how we set each of these up. For all of the DeepNet training, we use the initial condition as our input function, and we used 128 uniformly spaced sensors for that. And then or Saad presented, we have looked at both the Gaussian random field distribution as well as this alternative distribution here that's based on a sine function to where we sample an alpha and beta within -1 to 1. And that's driven by some other work that we've looked at, and I'll touch on here in a few minutes. We also start with all periodic problems of interest. And so to generate the data, as well as some of the comparisons coming up, for the advection diffusion, and the viscous-Burgers equation, we compare results and we train the DeepNet using a 128 mode Fourier solution with a time step of 1 to the -3rd for advection diffusion, and then viscous-Burgers would have been 1 to the -4th. And we trained DeepNet for a time interval of 0 to 1 for those 3. And as we switched over to Inviscid-Burgers, we'll present some preliminary results on that as well. For that, we used a Musil solution, and we solved it with 496 spatial discretization points And then to keep the same trunk, there's the same widths for our input function. We downsampled that higher order solution down to 128 spatial locations and then use that for DeepNet training. And since we were looking at sines, this distribution of sine of x, where sine of x forms a shock around t equals to 1, we trained DeepNet in that case too for a longer time interval. We went from 0 to 3.5 seconds instead. All right. So as Saad laid out, we have these basis functions now, and then how did we actually evolve them using a spectral approach? We first took the single value spectrum they've shown, where we have the very nice hierarchy and decay. And if you remember, once we get to about 10 to the negative 13th on the singular values, the corresponding basis functions largely become noise. So what we did as a form of model reduction here is we set a singular value threshold of 10 to the minus 12th, and we capped that as our limit to the number of basis functions we would use to then evolve the PDEs. After that, we used a more traditional spectral approach to really define our expansion in terms of these basis functions. And then due to our construction, we utilize the fact that it's orthogonal and orthonormal to then project and obtain a system of ODEs for the evolution of each of our coefficients. But you probably also noticed in some of those earlier slides, and it's not quite as easy to tell here, but our basis functions do not individually satisfy the boundary conditions. So that also is one of the reasons that led us to use a singular value threshold here, because we needed to reserve one of or two, depending on your number of boundary conditions. We reserved those final, say, n minus 1 coefficients to actually set our boundary conditions at each time step. So we'd evolve first 1 to n minus 1, solve for n based on satisfaction of the boundary condition, and then step forward in time using a Runge-Kutta scheme.
It's called the tau method, Brek.
Right, yes, that's
That was a tau method. Yeah.
Yep, exactly. I just wasn't sure, like I said, I know Boyd and then sometimes say Galerkin and then the other says tau, so.
No, Boyd, we go with the original, my mentor, Steve
Okay.
Orla.
That's what I've been calling it too. That's good to know, thank you. And then for our inner products and everything, since we use Legendre polynomials above, we use Gauss-Legendre quadrature, so the Gauss-Legendre grid, and then auto differentiation was used for all the derivatives that we needed to take. And similarly to our training, for the advection diffusion equation for our Runge-Kutta scheme, we used the time step of 1 to the negative 3rd, and for the Burgers equation, 1 to the negative 4th. Okay. So first of all, we have the advection equation, and again, it's a periodic boundary conditions on the domain 0 to 2. And here we're looking at an initial condition that's directly from that distribution. So sine of x and basically the generating function. And we have on the left here the 128 mode Fourier solution. And then the right are only using 30 of our custom basis functions. And you can see in the eyeball norm, we have very good agreement. But also when we come down and actually look at the relative error in a 2-norm sense, and this error is also based on still using 128 spatial locations so that we can do some sort of, like I said, model reduction. We have an average error over that 10 seconds of about 1.4 to the negative 10th. I can start this too. So within that distribution, using something that DeepNet was trained on for 0 to 1, and that same distribution, we can then take our custom basis functions, set up those ODs, solve them, transform back, and we can extrapolate for long times while maintaining very good agreement with the 128 mode Fourier solution. So the previous result, we did a little bit of extrapolation in time. We also looked at, similar like we showed above, for the advection equation, again, using the exact same 30 custom basis functions, no changes to that. We then looked at, can we use an initial condition that falls outside of that distribution that was used for the DeepNet. So for this, we use the exponential sine x. And similarly, the 128 fully mode solution versus the 30 custom basis function solution, at least eyeballing, we have very good agreement. We do, when we go to the relative error, we don't do quite as well as we did previously on something that was generated from the candidate basis functions from DeepONet trained on that sin of x distribution. But we do still achieve over that 10 seconds and an average error of now about 4 to the -8. So a slight decrease, but we still have very good agreement over that long time, showing that not only were we able to extrapolate in time, but we could also go outside, slightly outside that function space for which we trained DeepONet. So we also looked at the advection diffusion equation as another linear example, viscosity of 0.1, again, periodic boundary conditions. And now we went back into back into the distribution initial conditions. And similarly, what we saw previous, very good agreement, relative error still 4.1 there to the -9th over 10 seconds. So again, not to go too far into the linear PDEs. Similarly, advection diffusion equation again, we went outside of distribution to see if a slightly more difficult problem, or slightly different, I should say more difficult, slightly different problem, if we would achieve the same quality of errors. And indeed, eyeball norm again, and considering the error relative to norm error at 128 solution locations, we still get an average error of that 10 seconds of 2 to the -8. And we see good agreement as we evolve the solution in time too.
Brek, just to clarify, now you're using the advection diffusion equation for the base generation too also, right?
Yes, correct. So we would have trained the DeepONet on the advection diffusion equation between 0 and 1 on that same distribution.
With the same viscosity.
Yes, yes, same viscosity too.
You didn't try to extrapolate for different viscosities then, right?
We have a little bit with viscous-Burgers equation, and we have found for other values we can do some extrapolation there too.
Okay.
But yeah, so here I should have mentioned that. Thank you. We're using 28 custom basis functions here because in our training and our procedure, we find that that threshold is slightly higher now. So then we moved on to some nonlinear PD tests, and we went back to sin of x, still a viscosity of 0.1 here. And this is the case where we have tried some other viscosities and lower viscosities, and we can do some extrapolation. We do not show those results here though. And with this nonlinear term, we've approached it in 2 ways so far. For these results, we're still using the triple product integral, which naturally does not scale very well as you deal with that tensor. And we've also used a pseudo-spectral type transform to where we bring it to real space, do some Chebyshev differentiation, and then bring it back. We're also looking at kind of developing a fast inverse transform using DeepONet to further avoid that issue. But even with the triple product integral usage, and for a nonlinear problem, that was where DeepONet was again trained for the viscous-Burgers equation between time 0 and 1, and that exact viscosity, we still get at least in the eyeball norm very good comparisons. The relative error we don't do quite as well as we did with the linear problems, but we're still an average here error over 10 seconds here of about 6.5 to the -5th, which again, if we looked at this typical DeepONet, you would see similar to what you did previously with what Saad presented. So we're still keeping several orders of magnitude below what we would have achieved otherwise, even with extrapolating time with this method. So I should have started that. Let that run.
Brek, can you say at what time was this this basis was obtained?
These were all obtained at time equals 0. We took the trunk net here and sampled everything at t equals 0.
Okay.
Yeah, we haven't, Saad's done a little bit of work, like you mentioned, sampling them at different times to get further improvement, but these results are still all with pulling it out at time equals 0.
Right, because this will be important for the nonlinear case.
Mm-hmm. Yeah, and that's what we haven't had a chance to try that. That's one of the things we're working on that for the nonlinear case, like Saad was mentioning, because that will be interesting. And then again, like we said previously, we'll try a different initial condition that's outside the distribution using our method. And now we actually have a way that moves out of the domain, comes back in, as well as decays. And we see similar behavior in the error to where the average error is about 3.47 here, 3.48 to -4. So again, we don't do quite as well as we did on something that was within the distribution, but we're still able to accurately evolve it and stably for a very long time. So finally, motivated by some other work we've been doing, we want to see how this would work for the inviscid Burgers equation. So we trained the DeepONet, this time using that Musil solution that was downsampled to our sensor locations and a periodic domain 0 to pi, the same sign of x initial condition, which generates a shock at around time equals to 1. And if we look here, we now have 92 custom basis functions. And the other thing to note is DeepONet this time was trained between time 0 to time 3.5. So we trained for a longer interval to try and do a better job of capturing the shock since we knew it occurred around 1. And for some of the other initial conditions, it'd be even further out. But what we see between the two is we see nice agreement up to the shock, which is evidenced here by the error too. But as we approach that shock, the average error begins to go vertical. So it's not that value is not a great representation of what's actually happening. And not only does it go vertical, in this video here, that's slowed down to about 0.1x. I think it stops beforehand. Let me pause it. Whoop. Windows open. Well, it's not letting me do it. But if that runs, you'll see we begin to have some spikes at the edges here, and then shortly after the solution becomes unstable. So we're able to evolve this basically up to the point of shock formation. But what we're seeing is there's really no way to eject the energy that would be eaten up by the shock. So we get this pollution of the solution and then unstable results ultimately. So one way to address this is to introduce the concept of memory, which I believe will be a talk coming up in a few weeks. More on that. But that memory, what that would do is allow us to eject energy out of the resolve scales that we're looking at into the resolve mode, so we can capture that cascade of energy out of the system. And that's also where this hierarchical structure comes back into play, because now that we have that, we can use those model reduction formalisms and define a projector, that allow us to set all the unresolved coefficients exactly to 0 because of that spectrum and decay, and allow us to do like Meuris-Wanzig and that type of thing. And we've done some work where we used perturbative renormalization and had very good results for the inviscid Burgers equation. So this would be a good context to look at that and try it here. Can we apply those same approaches to where we look at a bigger system and make sure we can capture the energy comparison up to that shock, but then once we've done that and set up our model, we can evolve it for a very long time, stably and accurately. So that's something we're definitely looking at with this. And for completeness, we did show the other initial condition, which develops the shock slightly sooner, and we see very similar results here. That we do well, even though it's become skewed based on the pollution of the solution. We do relatively well from the identified basis function from DeepONet up until the point of the shock. But once we reach that shock, we then have the same issue where we can't deal with the energy cascade and it ends up just building up.
Brek,
So
there is are you familiar with the spectral vanishing viscosity?
I have never used it now.
No, that's okay. So it's a rigorous paper by Aitan Tadmor long time ago. So he shows that for the inviscid Burgers, any spectral method would get spectral accuracy if you use the spectral vanishing viscosity. So basically, it's a viscosity that is defined in terms of the mode. It has some parameters. So you put like a mode-dependent viscosity on the right-hand side, which of course helps for the entropy condition also. But if you look at the original paper of Aydar Tadmor, you will see, because even if you use a Fourier method with thousands of modes, you will not get this. So you need to use, and it turns out it looks like a filter in model space. You filter out the upper 1/3 of the spectrum.
Okay.
But it's a very easy implementation.
Okay, thank you. Yeah, I'll
So you have to do that in your, not on the DeepONet, but on the spectral projection. When you do that, you have to add that term. Otherwise, you wouldn't. Yeah. So it's really the spectral method that suffers.
That makes sense.
I have it in my book, but the original paper of Aydar Tadmor is very nice. Maybe Panos knows it.
Yes,
Thank
thank you, George. I know that paper, and that's why Saad Brek told about introducing memory, which also the spectral viscosity there that Eitan introduces is a kind of memory, because it helps you to get the entropy condition, etc. It's from 1988, the paper.
Yeah, a long time ago. Yeah.
Yeah, I'll send you the paper. Thank you, George.
Okay. Yes. Thank you both. Okay. So, all right. Oh, we're there. So, in summary, what we found is that DeepONet does provide very good candidate basis functions. It does a great job on its own, interpolating within the range of training, but also we can use those trunk nets to go down this approach. And once we orthonormalize them, it allows us to have very accurate evolution for these PDEs we looked at. We've also looked at doing this in a more discrete fashion, using vectors and using kind of discrete quadrature rules. And we've had some good luck with that as well, but you're limited. You can't do the approximation theory, some of those other bounding things like Saad showed. But we have found that for a certain class of problems, we've actually got slightly better results than some we presented here. But again, using the vectors comes with a whole slew of different issues, whether it's approximation theory or numerically carrying around all vectors as it comes to efficiencies. And one thing mentioned earlier is that we still need a fast inverse transform, that we can go from custom basis function space back to physical space, so we can deal with those nonlinear terms much more easily. And that's one of those things that can be done again by utilizing the GrADE structure for the DeepONet, to where we'd take the expansion coefficients, plug those into our branch, and then our input to the trunk would be a spatial location, and we could have that function returned ultimately. And then future work, or additional future work, is some of the stuff I was alluding to at the end of his portion, to where we need to do more work on generalizing this to higher domains, and how do we deal with some of those quadrature rules as we go to those higher and more complex domains. And then with that, that's it. And then first of all, thank you for giving us the opportunity. We really appreciate it. And if you have any questions, please let us know. I think Saad's still around too, so we can either part of the talk, if you have a question, please let us know.
Great presentation. Thank you guys, both, and Panos, thank you. This is, I think one way to put this in perspective, and I've been thinking about special basis for all my life, but I remember one of the second PhD I supervised at Princeton with Paul Baccio was how you can create Stokes eigenfunctions, but not just from the Stokes operator. We make the operator singular to look like a Sturm-Liouville problem.
Yep.
Then you actually get, I don't know if you know that paper, Panos, but so we created basically singular Stokes eigenfunctions which work like a charm at very small Reynolds numbers.
Yeah.
But the moment the nonlinearity kick in, so later on, Paul, after his PhD thesis, tried to introduce the, because you break the self-adjointness and so on. So I think the way to spin it here is that you will create basis for this nonlinear operator, for the advection part.
But you are creating from the nonlinear operators.
That's what I'm saying. I mean, that's what the emphasis should be.
Yes, and that's why I think it
otherwise
works.
You have many ways of getting good eigenfunctions on special domains and so on.
Right, but I think that exactly because it uses DeepONet, which is trained for a temporal interval, even if you identify the basis functions at time t is equal to 0, they do have information from the evolution. So that's why I think they give also good results for burgers, because you identify very nice basis functions which take into account dynamic information about the evolution of the solution. And that's what I liked initially at DeepONet. I think it is a powerful framework there.
Yeah, one could be very creative actually, especially with the systems that that have non-stationary dynamics.
Mm-hmm.
Like the shock, the last problem actually, where you show the large, that's where the opportunity lies.
Yep.
Mhm.
Yep.
Yeah.
And also this is the reason why we wanted to stop with something where this breaks, because we want to find out, what are the limits and how we can make it better for such difficult problems like shocks.
Hey, can I ask you a question there? This is really great talk. So you're working with global polynomials, which makes sense if you're targeting spectral schemes for ultimately working in, but did you think about working with like different types of approximators like spline spaces, or like if you're looking for solutions with reduced regularity, right, you're kind of setting yourself up to run into an issue when you hit these shocks, right? Have you thought about other kinds of building blocks?
That's a very good point. Yeah, but so when we looked at getting functions from just the quadrature values that we initially had, it just seemed natural to go down the route of projecting them onto polynomials because that procedure can be done pretty accurately. But yeah, we can absolutely take a look at local methods, splines, and as such, and see where that takes us. Yeah, that's a good suggestion.
Thanks.
I think what Nat's talking about the splines is actually a good idea also for domain decomposition.
Yeah, in that case, it works even better. Agreed. Totally agreed.
Thank you, Brek and Saad. It was a really amazing and a very informative presentation.
Oh, thank you. And thank you for inviting us and giving us this opportunity.
Thank you very much.
From data is salivating because she says, I can do that for crack propagation. Find good basis for crack propagation.
Right.
That will be great, right? We'll have what is the ideal basis for crack propagation? Let the opponent tell us.
Exactly.
All right.
Do we have more questions for the speakers? So if we have no more questions, let's thank the speakers. Thank you very much, Brek and Saad. It was really amazing presentation, as I already said. So yeah, with that, we could end the presentation. And we already started this day with a very sad news about Professor Bruce's demise. So let's all hope that his soul rests in peace, and let's have a very safe and happy weekend. Thank you.
Thank you, Professor Dada.
Thank you very much.